All right, let's get right into it. The D block elements, the transition metals, can seem really tricky, especially if you've got an exam coming up. But hey, don't worry. Just think of this as your own personal tutoring session. We're going to nail the key concepts in about 5 minutes, and you're going to walk away feeling a whole lot more confident.
Does this feel familiar? Yeah, if you've ever felt a little lost trying to figure out their weird properties, trust me, you are not alone. Our whole goal here is to just cut through all that noise and make it finally click.
So, here's our game plan. Think of it like a study checklist. First, we'll meet the metals themselves. Then we'll crack the secret code of their d orbitals. After that, we'll see why they're so colorful and magnetic and understand their chemical superpowers. And we'll wrap it all up with a quick pop quiz. By the end of this, you'll be all set. First things first, let's meet the stars of our show. Before we get into all the cool stuff they can do, we have to understand the one basic rule that explains, well, pretty much everything about them. Okay. This right here is the most important definition you need to know. A transition element has a partially filled d orbital. That's it. That one little phrase, partially filled, is the master key that unlocks every single property we're about to talk about. So if you remember one thing, make it that. Here's a good way to think about it. The main group elements, the S and P blocks, they're kind of the rule followers of the periodic table. Their behavior is pretty predictable. But the transition metals? Oh, they're the unpredictable, versatile artists, and it's all because of that special, partially filled d orbital. So how does this whole partially filled thing actually work? Well, to figure that out, we need to crack the code of their electron configurations. This is like the blueprint for everything they do. And here's the secret sauce. You see the ns orbital? That's the outermost shell. But the n-1d orbital, the one right before it, is super close in energy. That tiny energy gap means electrons can jump back and forth pretty easily. And that's where all the magic happens. This is the perfect example of our main rule in action. Look at scandium here. Its electron configuration ends in 3d1. See? It's an incomplete d orbital. That makes it a transition metal. But now, look over at zinc. It ends in 3d10. That d orbital is completely full. So even though it lives in the d block, by our strict definition, it's not actually a true transition element. Have you ever wondered why copper sulfate is that beautiful bright blue color? Or why some chemistry experiments have those deep purple solutions? The answer, you guessed it, is hiding in that d orbital. So let's just ask the question straight up. Why are so many of these compounds so colorful? It's definitely not an accident. There's something really fascinating happening at the subatomic level. It's a process called a d-d transition. Just imagine an electron wanting to climb a small step. It needs a very specific amount of energy to make that jump. So what does it do? It absorbs just one color from the white light hitting it. All the other colors that don't get absorbed bounce back to our eyes, and that's the color we end up seeing. So for example, a copper solution looks blue because its electrons are busy absorbing the energy from red light to make their jump. And this brings us back to our exceptions, right? Zinc, cadmium, and mercury. Their ions are colorless. And why is that? Because their d orbitals are completely full. There are no empty steps for the electrons to jump to, so no light gets absorbed, and we don't see any color. Now, those same electrons that give these metals their amazing colors also give them some really unique magnetic personalities. It all comes down to a simple question. Are those electrons paired up, or are they flying solo? Okay, there are two key terms here, paramagnetic and diamagnetic. But the rule is super simple. If an element has unpaired electrons in its d orbital, it's going to be paramagnetic, which means it's attracted to a magnet. You can think of each one of those unpaired electrons as a tiny little magnet itself. If all the electrons are paired up, then it's diamagnetic, and it gets weakly repelled. And this actually leads to a really neat, predictable trend. As you move across that first row of transition metals, the number of unpaired electrons goes up, and it peaks right at manganese, which has 5 of them. That makes manganese the most paramagnetic of the whole group. Then after that, the electrons start pairing up, and that magnetic character starts to decrease again.
So why does any of this stuff matter in the real world? Well, these unique electron properties give transition metals some serious chemical superpowers, and that makes them absolutely essential in all sorts of industries and even in biology.
One of their biggest superpowers is being amazing catalysts. And it all goes back to that tiny energy gap we talked about. Because it's so easy for them to move electrons around, they can lend or borrow different amounts. That gives them what we call variable oxidation states.
This flexibility makes them like the perfect chemical matchmakers, creating a new, easier pathway for a reaction to happen.
A classic example is potassium permanganate. In this compound, that manganese atom is in a +7 oxidation state, which makes it an incredibly powerful oxidizing agent. It's so powerful, in fact, that its ability to just rip apart chemical bonds is exactly why we use it as a disinfectant to purify water.
All right, you have taken in a lot of information. Now it's time to lock it all in with a quick pop quiz. You ready? See if you can answer it before I show you the solution.
First question, and it's a really important one. We've actually mentioned it a few times. So, why does zinc, cadmium, and mercury get kicked out of the official transition metal club?
And the answer is, it all comes back to our number one rule. They have completely filled d orbitals. No partially filled d orbital means they just don't fit the definition. Simple as that.
Okay, last one for you. This question really shows you the incredible range of properties in the D block. How in the world can chromium be one of the hardest metals while mercury is a liquid at room temperature?
The answer is all about the strength of their metallic bonds. Think of it like the electron glue holding the atoms together. Chromium has a bunch of unpaired d electrons that form a really strong glue. Mercury, on the other hand, has 0 unpaired d electrons. That makes its glue incredibly weak, and the bonds are so easy to break that it's a liquid.
So there you have it. The secret to their color, their magnetism, their catalytic superpowers, it all boils down to that one key feature, their partially filled d orbitals. It really makes you wonder, doesn't it? As we get better and better at controlling these unique properties, what kind of amazing new technologies are we going to unlock next?